Liability threshold is a Unit 2 concept that is typically given students some difficulty. In this presentation, I'll give you a view of liability threshold that I hope will make the concept less troublesome. First, we'll look at some basic statistics. Then we'll discuss the concept of a liability threshold. Finally, we'll apply this to human disease. When we look at the distribution of some characteristic in a biological sample, we often find that it follows what's called a normal distribution. Synonyms for normal distribution are Gaussian distribution, named after the mathematician who characterized it, and bell-shaped distribution because its shape is that of a bell in cross-section. Along the x-axis, from left to right, we plot some characteristic. For example, we could be looking at height, intelligence quotient, or blood pressure. These data are typically binned, which means we take them in groups. For example, if we were looking at height, we might have a bin for people between 5'3" and 5'6". Along the y-axis, we plot the number of people who fit in that bin. For example, if in our study we find 99 people who are between 5'3" and 5'6", we'd plot 99. All the curves on this page are examples of normal distributions. They all have a peak, which corresponds to the mean or average value. This is also the median, which is defined as the middle value. If we lined all the people up by height, the median would be the person in the middle of the line. It's also the mode, which is the most common value. In a perfectly normal distribution, the mean, the median, and the mode are all the same. This is what makes the left half of the graph a mirror image of the right half. These graphs are all perfect normal distributions, and yet they're different from one another. They differ in a characteristic called the standard deviation. This is a number that describes the spread of the curve. The flattest curve, the one at lower left, has the highest standard deviation. There's more spread in the population. The sharpest curve, the one at lower right, has the lowest standard deviation. Most individuals fit in a small range on either side of the mean. Here's where we unlock the power of these descriptive statistics. By definition, 68% of the individuals in the study population fit between the mean minus 1 standard deviation and the mean plus 1 standard deviation. The mean is represented by the Greek letter mu, which looks like an M with a long tail. The standard deviation is represented by the Greek letter sigma, which is like a circle with a tail at the top. You can confirm the 68% figure by graphing the curve shown here, then counting graph paper squares, or by drawing it onto a piece of paper and weighing the paper. You'll find that if the whole curve weighs 100 grams, the part between minus 1 and plus 1 standard deviation weighs 68 grams. The area under the curve is also the same as the number of people who have that characteristic. We can keep going with this. 95% of the people fit within 2 standard deviations. 99.7% of the people fit within 3 standard deviations. Just over 1 in 1,000 people make up the tails of the curve on either end. Most people's first encounter with a bell-shaped curve is the intelligence quotient, which measures a person's ability to blacken the correct circle on a Scantron sheet. Intelligence quotient was originally defined as someone's mental age divided by their chronological age and then multiplied by 100. So if you're 15 years old and you're an average 15-year-old with a mental age of 15, then 15 over 15 times 100 gives you an IQ of 100. Notice how this matches our definition of mean. By convention, the standard deviation of an IQ scale is set to 15. So, 68% of people have an IQ between 100 minus 15, or 85, and 100 plus 15, or 115. 95% of people have an IQ between 70 and 130, and so on. If your IQ is above 130, you're in the top 2.2% of the population, and you can join Mensa. We'll just check the previous slide to check that number. So you see that the IQ above 130, which is 2 standard deviations, is in the top 2.2% of the population, and you can join Mensa. There are even more exclusive societies for people who have, for example, IQ scores 5 or 6 standard deviations above the mean. The tail becomes very small at this point, and so these people are truly unusual. Another biologic characteristic in humans that follows a normal distribution is height. This graph is from a British site for school kids. That's probably why the average height in this population is 152 centimeters or 5 feet 0 inches. That's a very small population. On the other hand, we know from studies such as NHANES, the National Health and Nutrition Examination Survey, NHNES, that the average height for adult American women is 5 feet 4 inches with a standard deviation of 2.75 inches. That's 162 with a standard deviation of 7 centimeters. The average height for adult American men is 5 feet 9 inches with a standard deviation of 2.9 inches, 176 with a standard deviation of 7.4 centimeters. The NHANES is where we get most of our statistics on things like height, weight, and body mass index for Americans. Our class notes mention that blood pressure is normally distributed as well. Here's the data to back up that assertion. In this first graph, we're looking at systolic blood pressure. We expect a mean blood pressure of 120 systolic over 80 diastolic, and these data support that. Notice the data are not exactly symmetrical. Statisticians call this shape, with a long tail to the right of the graph, skewed. Why do you think the data for systolic blood pressure are skewed to the right, to the higher end of the scale? The data for diastolic blood pressure fit the normal distribution much more closely. Let's take a break from math class and go on to English. What do we mean exactly by a liability threshold? The dictionary tells us liability means, quote, the state of being liable, end quote. Well, duh. To be liable, on the other hand, is to be, quote, at risk of something unpleasant, unquote. This is a pathophysiology course, so for us, to be liable means to be at risk of pathology. A threshold is something that only carpenters and newlyweds think about. It's the bar on the floor under a doorway. In your house, most of the thresholds are low or maybe even imaginary. That's so you don't trip over them. A high threshold would be very difficult to get over. Only a few people would be able to cross a high threshold. That's also true of a high liability threshold. Only a few people would be unlucky enough to cross over the liability threshold into a state of being liable. This is a lottery you really don't want to win. The more you're over to the right, the higher the risk is for you. If it goes too high, you cross the liability threshold into disease. In short, you're in the crosshatch region marked affected. At left, we see a photograph of a man and a boy crossing a threshold in a park. At right, I've drawn a red line to indicate the tail of the bell-shaped curve. There's also a vertical line to mark the liability threshold. Now you're in the plane of the paper looking down the bell-shaped curve toward the hump of the mean value. The man and boy are crossing the liability threshold into disease. So for the last few slides, let's apply this to the graph that appears in your notes. Imagine we're looking at the liability threshold for a disease such as lung cancer. Your genetic makeup gives you a certain set point, a starting point for our analysis. You begin life with a combination of risk factors, some good, some bad, and that genetic complement is shown by the red arrow here. Next, we expose you to 2 packs a day of cigarettes. This moves you closer to the liability threshold. There are also examples of behaviors or actions that could move you further away. We're not considering those today. Finally, your work as a coal miner exposes you to a dusty environment. Now you've accumulated enough risk factors moving you towards the disease liability threshold that you've crossed that threshold into the realm of disease. The higher the threshold, the further you have to travel to get there. You have to accumulate more risk factors between the genetic and environmental causes of that disease. As the term liability suggests, you're at risk for something unpleasant happening, in this case a disease process. Because you've crossed the liability threshold, your potential risk has turned into a very real unpleasantness.